students. I hope you all are enjoying this series on vector calculus. This is an important topic when you prepare for IAS exams, or otherwise also this is very important when we want to use mathematics in different areas. So in this today's video we are going to talk about tangential and normal components of velocity and acceleration. So in last few videos we are talking about a particle moving in a curve, right? So if particle is in motion, so definitely it has velocity and acceleration, and then that velocity and acceleration both are vectors. So we would like to look at the components of those two vectors, right? So we have a curve, we have a particle which is moving along a curve x of t, okay, where t is our parameter, right? And till now you must know that these are the assumptions which we are making till now, that x prime t is not 0 anywhere, and then we also saw that x prime x double prime multiplication is also not 0. These two conditions are necessary for defining the uh, normal vector, tangential vector and binormal vector at every point, which we have done in the last few videos. So if you have not gone through those videos, I'll recommend that first please look at those videos. If you have an idea of what is a tangential vector, normal vector and binormal vector, then you can continue. I'll give you a brief introduction here also, right? Okay. So we saw that at every point we can define a tangent vector, a normal vector and a binormal vector. This tangent and normal, they are in the plane of the curve at that point, and this is called osculating plane. Okay, so we studied about these things in detail in last few videos. So now if xt is the position vector, right, so I would like to know what is the velocity and what is acceleration, okay, and I want to know these things along t vector, n vector and b vector. So I want to know what are the tangential, normal and binormal. We'll see that there is no binormal component, that is why the title tangential and normal components only. Similarly for at also I want how I can write it as a component times t vector, another component times n vector, another component times b vector, right? So I would like to find out these components. So that is my aim. So let us try to do that. Before that, you must remember this fellow s, which is our favorite parameter. So s was defined as you fix a point p, and then at any point the length from p to that point is your s. So basically we start from 0. So we have 0 to t x prime t modulus dt is our s parameter, and we know that ds by dt is nothing but this x prime t modulus. And okay, and for simplicity here we'll denote with s dot ds by dt and s double dot d2s by dt2, right? So let us see here what we are trying to do. So if you look at this quantity here, this is modulus of x prime t, right? So that means that's the modulus of velocity. So we come to know that ds by dt is modulus of velocity, right? And then we also have t vector is defined as x prime t, this is the definition of tangential vector, divided by mod of x prime t. So that gives us, this is nothing but velocity. So t vector is velocity times modulus of velocity, right, which is equal to, this modulus of velocity is s dot. So from here you get that vt is s dot times t vector. So this is a simple, very simple expression for vt. So from here we see that the tangential component of velocity, tangential component of velocity, component of velocity is s dot, and there is no normal and binormal component of velocity. right? So this is what we got from here, and this is what you have to remember, right? Now the similar thing we have to do for acceleration also. Let us do that. So let us have a similar thing for acceleration. So you must know that from where we should start. We should start by differentiating the velocity vector, because we know that acceleration is derivative of velocity vector, and we just saw that velocity vector is here. So that is dy by dt of s dot t vector, right? So that is our acceleration. So now you can use the product rule here to differentiate. So if we use the product rule, I can write it as s double prime t vector as such plus s dot dt by t, right? Now this thing we are looking for, like we know we want to separate it into components, so we'll keep it like that only. So we'll be just working on this fellow here, dt by dt. So let us see how we can calculate dt by dt. Any ideas? Do you think, like, do you have any idea that how shall I start? I want to convert it, right? So can I write it like this, dt by ds and ds by dt? Why so? Because I know from this Sennett formulas that dt by ds is kappa times n vector, right? So this is chain rule. When I go from here to here, that is chain rule, and then this is kappa times n vector ds by dt. So that is kappa times n vector ds by dt is s dot. So that is kappa s dot n vector. Therefore, our acceleration, which is here, becomes s double dot t vector plus s dot, and then we have kappa s dot n vector. So we get that acceleration is s double dot t vector plus kappa s dot square n vector, right? So we get tangential and normal component of acceleration, and you can see that there is no binormal components here also, right? So note that no binormal component both in velocity as well as acceleration, right? And also in velocity, if you see, we can see that the velocity is totally along the tangential vector that we expect also, right? When particle moves in a curve, right? So we know that at every point, at any point, the velocity is only along the tangential vector. If it is not so, then the particle will change its territory, right? Okay. So, so that means both, because there is no binormal component, therefore we can claim that both velocity and acceleration vectors are in the osculating plane. They are in the osculating plane. They are not having anything outside that plane. Okay, so do you understand what we are doing here? So basically, the only thing you are doing here is acceleration as a vector. You may know it in terms of I, j, and k cap, right? So this is one Cartesian system we have, but now we want it in terms of t vector, n vector, and b vector, because this is our personal Cartesian system. If you think it like this, for a curve we have, this is an intrinsic system of axis, which is very helpful, and we can use all sort of formulas. Okay, so you have to remember that uh, velocity tangential component is s dot, right? And acceleration tangential component is here s double dot, and acceleration normal component is s dot kappa s dot square, right? Now, because calculating kappa was not easy, we saw that, right? So we would like to have an alternating formula for this. For that, what you can do is, because generally acceleration is known to us, so if I just look at my acceleration vector, I know that is s double prime t vector plus kappa s dot square n vector. So if I look at the modulus, so that would be 80 dot with 80. So I can write it as s double dot t vector plus kappa s dot square n vector dot product with s double dot t vector plus kappa s dot square n vector, and then I can write it as s dot double dot square t vector plus kappa s dot square s double dot t vector dot with n vector plus kappa s dot square s double dot n vector dot with t vector plus kappa square s dot raised to power 4 n vector dot with n vector. Now look at these quantities. How much is this? How much is this? How much is this? And how much is this? You can write in the comment box. Okay, so this quantity is 1. Why? Because the t is a unit vector, right? And if you look at the second quantity, t dot n. So this quantity here is 0 because t and n are perpendicular. Similarly, this is 0 and this is 1 because of the unit vector n. So we get this equal to s dot square plus kappa s dot square square, that is equal to mod of this acceleration vector square. Does that make sense? Okay, in the beginning I have to write square because here it should be a square, right? Now what is this? This is tangential component of the acceleration. So this is the magnitude of the acceleration plus what is this? This is the normal component, right? Because normal component was kappa s dot square. So we got that normal component of acceleration is square root of magnitude of a square minus tangential component of a square. So this is what we got for the normal component, right? So we have to use these formulas for calculating the velocity and accelerations, tangential and normal components. The most important thing is you should understand what we are exactly doing here. So instead of having the velocity vector with components along I, j and k cap, we are trying to have the components along t, n and b vector. That's it, right? Okay, so let us do a problem. So we have that x of t is x of t, suppose x of t is your t comma 2t comma t square, and you have to find the normal and the tangential component of velocity and acceleration. So find tangential and normal components of velocity and acceleration. Components of velocity and acceleration. That is our question, right? So we have here, if we look at your xt is t I cap plus 2t j cap plus t square k cap, then your velocity vector would be x prime t, and that would be 1 I cap plus 2 j cap plus 2t k cap. That is our velocity vector. And you can also calculate your acceleration vector. This is x double prime t, that would be 0 I cap plus 0 j cap plus 2 k cap. So this is plain simple, right? We can calculate our velocity vector, we can calculate our acceleration vector from a given position vector, right? But now we are looking for this normal and tangential components. So now if you look at tangential component of velocity, because we know that velocity only has a tangential component, so that is equal to s dot, and what is s dot? That was the modulus of x prime t, right? So here is your x prime t, so modulus will be 1 square plus 2 square plus 2t square, so that would be 5 plus 4t square. So this is the tangential component of velocity, and normal component of velocity is 0. Normal component of velocity is 0. Right? Now we can look for acceleration. So tangential component of acceleration is s double dot. So that would be by dt of s dot. S dot we just calculated here. So that would be by dt of 5 plus 4t square. And if you differentiate, this will be square root of 5 plus 4t square, and then you have 4t. So this is your tangential component of acceleration, right? And now, so this is basically my a tangential, and now I am interested in a normal. So I have two choices. Either I compute kappa and do it like this, or I can use the second formula which we derived, that was modulus of acceleration square minus tangential component of acceleration square. So modulus of acceleration, we can just get it from here. You can see that mod of A is 2, right? So this would be 2 square minus tangential component we already calculated. So this will be 16 square upon 5 plus 4t square. So this would be 20 plus 16t square minus 16t square upon 5 plus 4t square. So that would be 2 root 5 upon 5 plus 4t square, right? So that is your normal component of acceleration, right? So I hope you understand all the things which we covered in this video. If you have any queries or doubts, please write in the comment box. Please share this video and subscribe to this channel. Happy learning. Keep supporting.